All right, good afternoon. My name is Jesus del Alamo. I'm the director of the Microsystems Technology Laboratories. And it is a pleasure for me to introduce Dr. Ian Young, who is Director of Exploratory Integrated Circuits at Intel Corporation and Senior Fellow, which is the highest technical distinction that Intel gives to its engineers. Ian received its bachelor's and master's degrees from the University of Melbourne in Australia and his PhD from University of California in Berkeley. And he has spent most of his career with Intel. Looking at his CV is really impressive because he has worked in so many different areas of integrated circuit technology, DRAMs, SRAMs, microprocessor circuits, photonic transceivers, CMOS RF chips, you name it, he's worked on it, and he has made very significant contributions. In fact, he has received 3 Intel Achievement Awards, and he also is an IEEE Fellow, has a bunch of publications and 34 patents in the last count that I saw. His recent work is of great interest, and he will be talking about today. It's about developing a uniform benchmarking methodology to identify Beyond-CMOS options in quantum nano-electronics and nanomagnetics involving a variety of new devices. Ian, it's a real pleasure to have you today. Thank you very much for coming.
Thank you very much. Is this? Can everyone? Okay, so thank you. Look, I am a circuit designer who has basically in the last 7 years moved to look at this Beyond-CMOS challenge, and so working and learning a lot about quantum mechanics and new materials and so forth. So I think what I bring is that bridge between the science and the engineering of circuit design for Beyond-CMOS computing. Dimitri is a member of my team at Intel. So another way to look at the title, and actually the title was this longer title, is we're exploring Beyond-CMOS, and what we're focusing on is energy efficient quantum nanoelectronic and quantum nanomagnetic devices for computing. We've done a lot of benchmarking of all of the research ideas for a new transistor, and they really have fallen into 2 categories of electronic and nanoelectronic and nanomagnetic devices. But what I'm going to talk about today is about what are the trends and principles, guiding principles for looking at these devices and selecting what are the winning options, the leading options to go really dig down into more research and pursue research on and eliminate the ones that are not viable. That's what I meant by principles and trends. Now, first of all, why are we doing this? Why would we be looking to find something beyond the CMOS transistor for circuits in computing? Well, first of all, as I said, we've done a lot of benchmarking and methodology. So we looked at Intel's technology from the 0.35 micron node all the way down here to the 14 nanometer node. This is based upon the publications, so I didn't use any non-public information, based on the IEDM papers that we publish on a regular basis. And so here is a 32-bit ALU. I told you we use a methodology to really look at computing with these devices, and here's CMOS building an ALU. And there's the energy per operation and the delay, all right? And so we can see here that there has been a period where we've got traditional Dennard scaling. This is the period of the 90s, and the 80s and 90s, and then early O's. And then we have a period of new material scaling. But what the main point is that we continue to make improvements in energy and delay. So everything's great. But the problem is with Moore's law, we get 2x times more transistors every generation when we do our technology scaling. So what we saw here, there was there's meant to be a shaded area here, but just looking below this line, we've got energy, we've got power density, watts per square centimeters on this vertical axis, and throughput in teraops operations per second. So this is a performance metric, and this is a power density metric. And this line is drawn at 10 watts per square centimeter, which is about a hot plate on a stove, which is that's probably a problem for a phone or a cooling in a data center. So above this, we see that we've gone above this in the 22 nanometer, 32 nanometer, 22 nano. So we're saying that we have a problem where the power density is too high and we need to be more energy efficient in the technology, or otherwise we can't turn all the devices on. We have to shut down and so forth. So that's the main point, is CMOS has got a challenge with energy. And as we're not decreasing fast enough, and power density is approaching this 10 watts per square centimeter. Of course, if I lowered the supply, I would reduce the dynamic power. But I can't lower the supply because, dynamic power, reduce the dynamic power, see that the capacitance times the voltage squared, the power supply squared. But if I reduce the supply, the power supply for CMOS, I get a performance suffering. So this is the performance, the delay increasing exponentially as I get near the threshold of the device. And of course, I could lower the VT, but then I'm going to increase the leakage. And we all know that there's an optimum energy delay, energy point to lowering the voltage to around, depends on the leakage, maybe 0.3 volts or 0.35 volts area is optimum for the energy efficiency, but not for that's the best you could get out of CMOS, okay? But we want to do, this is the reason why we can't do better than that is that we have this 60 millivolts per decade subthreshold slope. It's due to the thermal tail in the carriers of the MOSFET. We'd like to go beyond that. So we'd like to go really down below 0.3. We want 10x or more, 10 to 100x more improvements in energy efficiency. So CMOS is challenged with energy, but we've been here before. And everyone says, Moore's law is ending and so forth. Well, Moore's law started back here in bipolar days, 1965, Fairchild. And so it was bipolar. And bipolar went through an escalation in power, power flux or heat, right? And it made the transition to CMOS. Intel did it in the microprocessors in the mid-'80s, and IBM took the mainframes there in the mid-'90s, a very traumatic change for IBM. To change all of their bipolar ECL circuitry in mainframe computers to CMOS, but that was done. So the transition was done to CMOS in the mid-'90s. We're in 2017 now, right? That's not that many years, right? So it's been basically 30, 35 years of CMOS, and we're getting to this point where the heat flux is too high, the power density is too high. So we've got a transition to make. This is the question. This is why I'm doing this research within my group, is that we're looking for what's the next technology curve to jump to. And we believe that there is, if we can find a device that can switch at lower voltage. So semiconductor industry is faced with this situation before, right? So we've done some benchmarking, and there is a publication. I think I have it in the lower part of the curve slides coming up. But we benchmarked a lot of technologies. But first of all, we looked back at what the history was. And we saw that history back here in these days here, when we're in bipolar, ECL and TTL, all these were different logic technologies, circuit techniques to use the bipolar transistor to get lower energy. And then CMOS was down here. So my main point is that there was a trade-off being made. When we went to CMOS, there was greater than 50% lower power. But when we went to CMOS, it got slower. So this is the point I want to take. We didn't just say go to CMOS at the same speed as bipolar. We went to CMOS trading off speed for a big gain in power, right? So CMOS was much slower than ECL logic. So that was an improvement in the energy delay product, but there was a trade-off, 50x lower power for 30x slower. So I told you we did some benchmarking of Beyond-CMOS, and we've done this here. This is sort of where all of some 25 devices, TFETs, magnetics devices, and so forth. And the charge devices are in blue, electronics, spintronic devices. One of them, I don't plot all the spintronics, but one of the ones that's a leading spin option is in red. Basically, they're maybe 3x better in terms of energy delay product. These are there should be little light lines here, diagonal lines. These are constant energy delay product. But what I'm trying to say here is there's about a 2-generation scaling that we can identify in these Beyond-CMOS devices. But what's really interesting is this curve here, this slope, is a 10x lower energy, but at a cost of 4x lower power. That's a better value proposition than even CMOS was over bipolar. So while we haven't yet built these devices yet, but we're doing experimental work, fabrication, and so forth, and pursuing this, there is a potential opportunity. And I think this blue curve is going to continue to move down further as more research pursues it. Very important to do the research here. But there's a good value proposition for Beyond-CMOS, finding the next transistor or the next switch. So how do we go find that next transistor or next switch? What are the principles? And so out of this methodology that we worked on with Dimitri, we've gone through and extracted some basic principles and trends that we use to sort that. It's basically a litmus test, a set of questions to ask as you look at another device. The first is, beyond CMOS circuits, will we require CMOS? This is a very important thing to just take into your mind. We're not going to take CMOS, take it out of the fab, and bring in a new wafer with this new beyond CMOS transistor only. We have to coexist. It will augment CMOS. I mean, we'll still use it for the analog circuits and so forth, power delivery, clocking, and so forth, perhaps. So beyond CMOS will coexist, will augment, and be integrated with CMOS. So it's got to be compatible with that. Some devices should really utilize collective states because they're basically the most energy efficient, and also some of them have non-volatility, okay? Choice of an optimal energy beyond CMOS devices, be compatible with the interconnect. How are you going to interconnect these devices? So we have to do a transduction from some state variables like collective state to the interconnect, and we lose energy or delay in doing that. We have to comprehend that. So we have to worry about how we're going to do the interconnect, the input and the output to these devices. Low voltage devices, most direct way to low energy. So we're saying that, so CMOS is 600 millivolts, 700 millivolts. If we could work at, say, 100 millivolts, that's 5-6 times squared lower dynamic energy. That's where we're going to get the 10 to 100x improvements. I mean, there's no argument. I'll talk about that. There's no reason why we can't work at less than 100 millivolts. Start benchmarking and modeling with devices and build up the circuits. You've got to look at the circuits that you're going to implement with. How do you build the logic to do computation? You have to comprehend that. Majority gates might be a very attractive gate. They're very efficient, more efficient circuits, more complex computation can be implemented. So that's something to look for with some of these devices. We say use electrical interconnect for longer propagation spans. And we need have to think about what's non-volatility going to mean in the computing architecture. How can we exploit non-volatility since some of these devices have that capability? And last but not least is we also need to think about the future architecture. So we can look at general purpose processors, super pipeline microprocessor or CPUs or mainframe CPUs or graphics, for example. But what about neuromorphic? So we need to think about neuromorphic architecture. Does the device work for neuromorphic architecture? So these are the principles, and I'm going to go through individually, point by point, with some little bit more detail on that. So hopefully I'm not taking too long in the talk today. So first of all, collective states means potentially non-volatility. So what are the collective states? First of all, charge is not a collective state. That's what we have with CMOS. Tunneling FETs would be a charge-based device, not a collective-based state variable. But electric dipole, ferroelectricity, polarization, ferroelectric transistors, they are collective states. So they'll be non-volatile. Magnetic dipole is a collective state. Spin is a collective state. So some of the devices, such as the all-spin logic, spin wave devices, Nano-Magnetics, they can be non-volatile. Orbital states, such as the Bose-Einstein constate, the exciton, right? BizFET was one device that was researched for many years. So that's based on a collective state, but it's not non-volatile. Strain potentially could be as a collective state, could produce a device. It could, and depending on the type of use of the strain, it could be collective. So these are the kinds of state variables that we can build upon to build devices, or the materials principles that we can build upon, and it's important to look at those. So this is the field that we look at for Beyond-CMOS. And by the way, everything in Beyond-CMOS is going to be room temperature, 150 degrees C. None of this is cryo temperatures, all right? So no millikelvins involved. This is for real portable data center applications. So so I talked about non-volatility of collective states, but there's also the energy efficiency of collective states. Let me explain to you that. I'll give you an example between comparing an electronic switch, which is not a collective state, and a spintronic, a magnetic device switch. So here's the MOSFET. You have a source and a drain, and we have a gate, and we basically have a barrier. It's an over-the-barrier device, control device. And so here's our barrier. Well, the problem is that the barrier has the electrons have a distribution, a thermal tail. Let's look at what we need to have for supply voltages. So let's say we want an ion to I-off of something like 10 to the 7th or 8th. We need 20 kT barrier. This will give us a voltage of around 500, 600, 700 millivolts, somewhere in the 0.5 to 1 volt. We need only 200 electrons to get a reasonable signal on a capacitance. This means that every electron goes over the barrier, that's 4,000 kT of energy. Okay, so this is the amount of energy I need to basically send the electrons through the switch. If I look at magnetic device, a spintronic device, we're going to be almost non-volatile, pretty good, maybe a few, the stability will be, a year or more, 60 kT. Because it's a collective state, we only need tens of millivolts for this. And all 10,000 spins to produce a stable 60 kT magnet, they all go over the 60 kT barrier together, and you don't expend that cost for each individual. It's only 60 kT of energy versus 4,000. Okay? That's the difference between a collective and non-collective. Okay? And so the details of the equation, how we get the leakage I-on to I-off is related to the barrier, and the energy of the magnetic device is not related to the barrier. So we go through this, a list here of charge, electric dipole, spin, orbital state, whether they're non-volatile or not, whether we can, what's the writing principle, how do we switch it or turn it on or off? For electric, magnetoelectric, what is the voltage? And then what would be the reading? So we can see some of these magnetic devices, spin devices in sub-100 millivolts. The exciton devices, it's 300 millivolts. For electric devices, 50 millivolts. So we have a potential for low voltage. I mentioned that so now I'll go to that first principle. We need, beyond CMOS, we'll still need CMOS. So how are we going to do the power delivery? How are we going to do the clocking? We're going to need switches. So basically, turning on and off the supply of current is going to be needed. Here's an electronic device, transistor driving an interconnect. This is copper interconnect, another transistor. In the case of magnetics, if we're using spin transfer torque, we're going to have current running through the parallel and anti-parallel stack of ferromagnets to do the spin torque of switching. It's two states. We could look at ferroelectricity, where we once again have charging of the capacitance and switching of the polarization in the ferroelectric. Or in the case of what we've found with spintronic devices, magnetic devices, we can have voltage-driven switching of this ferromagnet. And this is much, much more efficient. In that case, we have a multiferroic, a material that's both ferroelectric and magnetoelectric, controlling the magnetism of a ferromagnet. So this is just saying that we still need to supply these charges or voltages to the devices. So the point I'm making here is that this is often forgotten about, that we need to have the power supply. We need to have the clocking. Now, what about the interconnect? Okay, so we're going to go down below 100 millivolts. And then, what about noise and signal to noise and so forth? Well, it turns out that the noise on the interconnect is basically the noise on the capacitance. It's the thermal noise. And we can do the KT over C noise calculation for a given technology node. This G makes a technology node might be a 22 nanometer node, so this G would be 22 nanometers, so forth. So that's how you get the length of the interconnect. Because as we scale transistors, the length of the interconnect scales also, right? So we've calculated here that as we scale, that we've still got, for that length of interconnect, we've still got 10 millivolts of less than 10 millivolts of noise, thermal noise. So, if we're 100 millivolts, 50 millivolts, or even 20 millivolts, we're still okay. So the point is that we can go to tens of millivolts of signal operation and still be okay. But there's a problem. How do I detect a 50 millivolt signal? I can't detect a 50 millivolt signal with a CMOS transistor. That's why we need to find a device that can detect sub 100 millivolts. And that's what we're after here with Beyond-CMOS. So I'm going to go into a third principle. Device choice needs to be compatible with this interconnect. I told you that interconnects, electrical interconnects, we could consider the noise on that could be quite small. Why would we do electrical interconnects, first of all? Well, we can look at spin, the movement of electrons spin in a metal, and we see that there's a lot of attenuation in that. We look at electrons, they tend to be very little attenuation relative to the scale of integrated circuits. So we conclude that we like electrical interconnect, but then how do we do a switch that works at such a low voltage? So one example is a device that we've been working on at Intel. It's involves a magnet. This is a ferromagnet in red. This is just a cascade. Let's imagine this is a multi-input gate. I've only got one input here, but we can have more than one input. And the charge comes in and charges the capacitance and changes the field in that ferroelectric polarization switches. When the ferroelectric polarization switches, the magnet polarization switches, and that switches the ferromagnet. And then on the other side, we have a conversion from magnetism back to charge, and we do that with an inverse spin orbit torque effect. We can convert back to charge. But I'm not going to have time to go into the whole detail of this, but I'm just saying this is an example of a device where we've thought through what about the collective state, the magnetism? What about the electrical interconnect? Well, we come up with a way of doing the transduction on the input and the output. This is examples and comprehends the interconnect driving, local interconnect, and the energy per bit. So a device like this can go sub 10 attajoules in terms of just the intrinsic energy of switching that and some local interconnect. Analogous to a transistor, intrinsic transistor energy, which would be much greater than that, maybe 10 times greater than that, 50 or 100. So we can build models for this, the dynamics of the input and the dynamics of the output, and we can see that we can switch this ferromagnet and so forth. That's the main principle here. This works at less than 100 millivolts with less than 10 microamps. Okay, so I've given just an example of a device, the Beyond-CMOS device. Now we need to go look at what kind of circuits can be implemented. How do we do the logic? So we have to think about building up circuits and benchmark those. And so what we do is we've built up a methodology of comprehending the layout rules. So those of you who do CMOS chips, we use design rules based on lambda rules, a minimum feature size and an alignment tolerance, right? So F is the minimum feature size, and lambda is sort of 2F. 2 lambda is equal to F, so the alignment. So we have some design principles. So we use that for laying out some of this. So here's a device, a majority gate. You'll notice there's 3 inputs and an output. And we're building up some adder here. We might build up, after building an adder, we might build an ALU. But we have to lay out the physical dimensions first and do the interconnect, because we want to get the parasitics, right? The capacitance of the interconnect, or the how much distance let's say it's a spin interconnect, how far the spin has to propagate. So all of those go into some equations for the dynamics of switching the magnet, the dynamics of charging some interconnect, or propagating in an interconnect. It might be a domain wall moving in an interconnect, another kind of device. And so all of the physical attributes of the behavior of the logic come from the physical layout, right? And then we have to put in the principles of what affects the time and what affects the energy of propagating that. So very important to think about the circuits. That's the main point. And this is just the calculations for delay and energy as we build up these logic gates. And with this, we've benchmarked some 25 Beyond-CMOS devices. and looking at the current versus the voltage, as we look at all of these devices, what we see is one learning from this is go to low voltage. I made that point already in the talk, and the data confirms that you know, the low voltage devices here are very attractive to us. They have low current and so forth, and we'll see the performance in the later slide. What else do I want to say? So just keep in mind, blue is always the electronic devices, such as tunneling devices. Green, these two green dots here are high performance CMOS, and then the low voltage CMOS. We can take our CMOS that we have in production that might be used for high performance, we can use it at low voltage, like 300 millivolts or something, so, and benchmark that. Okay. So spintronics enables the lower voltage. All of these red dots here are the spintronic dots, and the charge devices are up here. Then as we look at energy versus delay for a 32-bit ALU, arithmetic logic unit, we see that some of this trade-off I was making before. So here's the blue, there's the charge devices. There's the CMOS. Notice the CMOS is on the same energy delay curve. Remember, this diagonal line is a constant energy delay product. Makes sense. This is the same technology, just operate at a different voltage. The tunneling devices, you know, maybe a 2-generation lead ahead of CMOS. For the this is a transparent, equal benchmarking comparison. Same design rules, and so forth. So apples to apples. Lithography technology node is the same. So we see that the red dots, some of the spintronic devices, we have two categories. We have this one's based on spin transfer torque, and this other group cluster based on magnetoelectric. And that's the point I was making earlier, which is spin transfer torque is very inefficient because we've got all this current flowing to do produce the torque, and we've got all the Joule heating from that. So there's not a lot of efficiency. It depends on the polarization of those electrons and so forth. Magnetoelectric was found to be much more energy efficient, as you can see from the axis here. But the point is that spintronics devices are slower than the electronic devices. That's the other takeaway. And that's where we get into this trade-off. What's the right trade-off? So tunneling FETs, energy delay is better than CMOS, but the magnetoelectric devices and the spintronic devices, magnetoelectric spintronic devices are slower but lower energy, and they're non-volatile. So as we take some of those 25 devices and go through the benchmarking, we learn some interesting things. Let's take, for example, building the one-bit adder, the beginnings point of building the adder. If we do this with CMOS transistors, it might be 28 transistors. If we do it with nanomagnetic logic, where we can use majority gates, it's just 3 majority gates. If it's all spin logic, just 2 majority gates, or if it's spin wave device, 1 majority gate. The point is, depending on the device we're looking at, we have some neat tricks that we can use to reduce the number of gates to implement the function. So some of the points to be made about Beyond-CMOS devices is they produce functions, not just switches, okay? Fewer devices for the same computing function, and that's as we go through this sequence. What about density? Okay, so you know, when you look at transistors, you know, these all require the layout, but when we get into some of these all spin logic gates or some of the spintronics devices, we're building a majority gate, and that's equivalent of a number of transistors. So there is an advantage in terms of layout density with some of these technologies. So here's power limited area. So basically, this is the area of the logic. And on the vertical axis, we see the delay. By the way, what would power limited area mean? So let's say I have a limit of 10 watts per square centimeter. If I exceed that 10 watts per square centimeter, I have to spread things out and lower it. So therefore, the area grows. But if I'm very efficient and lower than 10 watts per, then I can be more dense and so forth. So that's the point of this axis here. What we see here that is the spintronics devices very dense, but their delay, as I indicated earlier, is higher. Their delay is longer than the electronic devices. But that means that we can use more devices in with spintronics, and we can use more parallelism to get the performance. Okay. Now, I mentioned to you kind of earlier on in the talk about the electrical interconnect and why we liked using electronic interconnect versus spintronic interconnect. This slide actually probably should have moved it earlier in the talk. This is number 7 of our bullets. Makes the point about the spintronics for interconnect. We're looking here at spin interconnect in a metal, the propagation length, it's only microns, 1 to 4 microns, and the energy per bit to propagate that distance. And we can see that very quickly the energy exponentially grows as we go up in distance, and that's because of the spin flipping and the attenuation of spins. Now, as in electrical circuits in CMOS, we use repeaters to go longer distances. We can use repeaters here, and we can use all-spin logic as a repeater. Regenerates the spins. You know, we detect the spins. We then inject the spins again after restoring the state. And this is 1 repeater, 2 repeaters, 3 repeaters. And we can see how we can push the distance out further for better energy efficiency. And so this is a win. This is more energy efficient, say, than 1 repeater, or this one. But we can see here that relative to electrical interconnect, which would be way down here, this is just the transducer involved with regenerating. So this is the cost of doing 1 repeater and just basically amortizing the cost of the transduction to repeat. But electrical interconnect would be much, much lower in terms of that distance. Yeah, would be basically hard to see it on the curve. So that's led us to the electrical interconnect as being the solution. So they're limited by this high attenuation with length compared to electrical interconnects. So we talked about this power density issue. So here's a benchmark here of the power density, watts per square centimeter in the vertical axis, and throughput on the horizontal. I already kind of alluded to this earlier in the talk. And what we can see here is this 10 watts per square centimeter. If we benchmark, we see how some of these devices, the charge devices, tunneling IT, or it's a tunneling FET, the Van der Waals and CMOS, they're all limited up here at the 10 watts per square centimeter power density. And the spintronic devices, some of these spintronic, this is less efficient, they're more efficient. Their power density is much, much better. But still, up here, these charge devices, the blue, are getting the highest throughput. But some of these devices here are getting the high throughput and the power density being low. So this is where we see the fertile area to do the research and to pursue. And as you see, one of the spintronic, this is the spintronic device I introduced earlier in the talk based on the magnetoelectric switching. A tunneling FET here. So the main point is that tunneling FETs rival CMOS in throughput at lower power, but this magnetoelectric, once again, I'm repeating myself, they have the advantage of very, very low power. The question is, what's the trade-off of performance, speed, throughput versus the power? And it looks like to be something of interest here. So now I'd just like to talk about non-volatility in computing. So what's the potential benefit of non-volatility in computing? Well, as we look at microprocessors today, let's just take a look there and see how not having non-volatility in the computer, in the CPU, basically causes us to have to do more complex power management. So at the top here, we basically have our SRAM cell, and we're doing some computation. We're reading bits. We're doing some computation here. So this is time versus power. And the gray is indicating we've got activity. And then we go into this. We're not got any computing to do. We're going to shut things off, turn off the logic, and then we come back again later. But during this short time where we're turning off the logic, we have leakage current. So we've got all this time, depending on how long we're in standby, we have this DC leakage current flowing. We can see things expanded out here further. For example, this is, we've got the leakage going on here between these compute cycles in this part of it. But here, we do some very sophisticated, I call it sophisticated, I think it's, it's a lot more complex. We have to go and save the state, take it off chip, put it into memory that retains state, and then bring it back. And now we can turn the power supply off completely, And there's no static SRAM power, there's no static logic power. Everything's shut down, so the chip's not consuming any power, but we're saving the state of the computing. And then when we need to do computation again, we need to restore that state and start up again. So this takes time and energy to save the state and to bring it back. So if we had some non-volatile devices in the logic, we can basically do the computing. So here's an example, say MRAM. Let's say we had the MRAM or RRAM on chip. We can save the state in there, shut off the power supply, not have to take the state off chip into a non-volatile memory, and we can be no leakage, and then we can turn on the power supply and continue again. So that's the advantage of having the non-volatile memory on the chip. And so here, just comparing this, all this leakage here and the save, restore, and everything is gone away. Okay? So that's ideally what it is, but it's a little bit more complicated than that, because when we save the state, like in here, we have to write into the memory. So we've got to write into MRAM or RRAM versus SRAM. And SRAM is very efficient, but as I said, it's leaky. So we've got to go off chip. So I'm going to go off chip, save the state. That's going to take some time. I've got to weigh up the energy to move all that data off chip versus how much energy it is to write into that non-volatile memory. So we talk about a crossover time, a break-even time of where the cost of writing into the non-volatile memory, which is much more than, say, writing into SRAM or something, is attractive relative to the cost of moving the data off and moving it back. So that's what we've done here. As I said, we're trying to find a convincing argument for going with the non-volatile elements on the chip, and we've got to comprehend that leakage and that energy to write the bits. And so here we're just studying, let me just go through this graph here. This is meant to be the power normalized, assuming certain activity factor. And then this is the amount of flops that we get, floating point operations per second. And it really depends on the case. So if we had CMOS and the energy per switch or transition is 1 femtojoule and the leakage is this, 1.2 nanojoules, that's one case, and that's the gray case here. But if the dark blue case here. And then if we have much lower leakage CMOS transistor, we get a little bit more lower normalized power. But because of the fact that we're going to have basically a hard limit on the power dissipation that we can go to, if we exceed that limit, so we're going to say flops at 2 nanojoules per flop. If I exceed 2 nanojoules, and I might exceed it due to leakage, I can't get any more flops. So anything below this power, I just get no more operations. But if I go to something like a non-volatile logic device, 1 femtojoule, the same as the CMOS, but no leakage power, I could be all the way, I could get down to this. I can basically delve into the lower power operation, so longer battery life and so forth. But as soon as our non-volatile logic device has any kinds of leakage, we lose that performance at the low power. So it's a little complicated, but we've also got to comprehend leakage, dynamic power, and activity factors is the point I'm trying to make here. So I'm getting close to the wrapping up of the talk. I have one more principle that's worth looking at, and that's to look at the architectural aspect. And so one thing is with the artificial intelligence, neuromorphic computing, that field is very, very active and exciting right now, an area of great promise, and it's already showing itself. So we had to benchmark towards the other architectures that are not just general purpose processing, like microprocessors. And one kind of circuit function that is common to neuromorphic computing is the cellular neural net. And what we found is that this was some work done by Professor Naimi and his student or postdoc at Georgia Tech, took some of the benchmarking that we did in terms of the Beyond-CMOS devices, but applied the methodology towards the cellular neural net operation. And so this is no longer an ALU, it's a 4-weight, 10% input noise, 90% accuracy cellular neural net. And we see how the spintronic devices and the spintronics, it changed on this. Light blue is the spintronic devices. the CMOS is in the green, and the tunneling FETs are now red. So the tunnel FETs were blue before, but now they're red. So basically what we see is the spintronic devices here, they come into their own when we start looking at neuromorphic computing, the cellular neural net. And the reason why this is the case is that the spintronic device is very good at making a majority gate, high fan-in, and that's a thresholding logic function, which is very amenable to the neuron function that artificial cellular neural nets. See how this has basically 9 inputs, right? Eight inputs. So it's large fan-in kind of operation, and it's a thresholding operation that is done here. And so we're finding that this is an architecture that might be very amenable to the majority gate kind of logic family. So here's the conclusions. Trends in the benchmarking of Beyond-CMOS quantum nano-electronic and nano-magnetic devices have been introduced, the nine principles I showed. And if we follow those principles, we'll have a better job at finding the practical devices to go off and pursue in research. It did actually provide these promising directions, both the materials, the devices, the circuits, and the architecture. I've covered you from all of those, starting with the state variable, devices, circuits, and now architectural options like neuromorphic. So the question is, where do we focus the research effort out of the many important thrusts? And I think with these principles, we're getting a head start on to sort out the wheat from the chaff, if you will, focus on the right devices and not pursue devices that don't show promise for Beyond-CMOS computing. So I just have one little additional, couple of things. So the main point is magnetoelectric-based logic and neuromorphic Beyond-CMOS circuits are very attractive for this pursuit. And I think if you also want to read more about what I've talked about, there is a paper at SDIRC this year, 4 pages, so it's not a short 1-page abstract. So it'll go into a lot of the graphs and so forth and explaining of this. And I think the slides will be left on the web. But the paper will be something you can actually read, since the video wasn't done. So that was my decision. So there's one other thing I wanted to add. If you're interested in this field, 2 reasons I want to talk about this. This is a new journal on exploratory solid-state computational devices and circuit. Its scope is multidisciplinary research in solid-state circuits using exploratory materials and devices for novel energy-efficient computing beyond standard CMOS. This is a place, it's been going, this is the 3rd year it's been publishing papers. Some of them are getting very highly cited. But what I wanted to say was this is a place where you could either publish if you're going to pursue devices in this area, but if you're also just a circuits or a technology, a CMOS or whatever, if you're interested in the semiconductor industry and where the future is going, this will be the place where you can actually read more about what's happening in spintronics, what's happening in nano-electronics, and so forth. So I think this is going to serve both as a place for a community of Beyond-CMOS researchers to publish at, and it's also a place where the future engineers and scientists in the field of semiconductors will be able to educate themselves and so forth. So this is the scope for that journal. So I just thought I'd mention it since I am the editor-in-chief of this journal. So, and all right, thank you.
Thank you, Ian. We can take some questions now. Please wait for me to bring the microphone if you want to ask a question. Yes, Alon.
Thank you for the great talk. So my question is, how do you think the fact that we are moving from general purpose CPU to based on the customer requirement, application driven. So if different customers or different application will require different technology, each technology will require higher barrier to develop. Mm-hmm. You will need more resources, especially when you are talking about collective phenomena, which have higher reliability threshold and stuff like that. How do you see this converging?
Okay, so I think, as I said, first of all, this technology will augment CMOS in the beginning. The way computing is going, there's a lot more specialized computation on chips now. We have engines for graphics. We'll have engines for codecs and recognition and signal processing. We'll have engines for artificial intelligence. So there will start to be more of these specialized applications. So it's sort of what your question is. But where there is an application that is really, really dominant and a very, very big part of a chip and a significant consumer of power on that chip, that'll be the application that we'll go after. And so that will be where some of these devices may offer a great potential, like more than 10x improvement in performance or energy. And so that will be it. But we won't do everything. Right? So it's going to really just be very limited in scope for the big value proposition applications. And so that's how I would look at this in the beginning. Later on, I don't know. I don't know how it will go. But certainly for the diversity of application-specific, custom chips, that'll stay with CMOS. But if it's really an application that is very, very critically dependent on low power, well, and if it's a high enough volume application, then maybe this will be an area that'll come to fruition. So, good job.
Yeah, thanks, Ian. It was a 5-year lesson in 1 hour. So
yeah.
When you had the memory, the non-volatile memory on chip, then that was basically allowing you to sort of solve the problem when you had activity, when there was low activity, if I got that right. So, that seems to, I think you said that's sort of that happens a lot in processors.
Right. It's a pretty.
So what happened? I couldn't quite figure out the right time for these non-volatile cells. But my question would be, why can't we put non-volatile memory on CMOS?
Oh, we can. That's going to happen. And there is a couple of options. It's RRAM, MRAM, ferroelectric RAM, whatever. Right. So that's going to happen. It's, for example, TI, and I can't remember, has microcontrollers since 2001 that has non-volatile, and for this very reason that they needed to be able to save state, turn off and save power. The issue is that the circuit design guys on the high-end microprocessors got pretty sophisticated in doing all this movement of data off, save it, power down the cores or power down the whole chip, that the cost of writing that MRAM or ferroelectric RAM or RRAM, that's orders of magnitude more delay and more energy than just CMOS. Now, I have the cost of the energy to go off, over the wires and off chip, but it's, what I'm trying to say, it's nanoseconds, sometimes tens of nanoseconds to write this MRAM, and I can't think of the femtojoules, but a lot of joules. So that's the break-even point. I can move data off chip, write it into SRAM that's got a power supply, or I can write it on MRAM on chip, and there's got to be a value proposition for that. So that's what the trade-off is.
So then just one more follow-up.
They need to be faster. These non-volatile memories need to be faster and more energy efficient is probably the takeaway.
But that's the same, but in using them with the non-conventional, with the spintronics processing elements, it's going to have the same problem.
Because we have CMOS or what?
Doesn't matter what it is, right? Well, because you're going to use the MRAM, you're using it to solve the activity problem.
Right. But
you can either take all the data and put it off chip like they do in CMOS. If you have the spintronic devices, you still have the same problem. The MRAM didn't get any better, so you're still going to be better to take it all off chip.
Right. So that's not a value. So we wouldn't do it.
So the problem is working on the non-volatile RAM and get the right speeds down. And
Yes, right.
Okay.
Oh, yeah. So that's what I had the title here is, we need to have a convincing non-volatility paradigm, proposal, hypothesis for computation. And I'm saying, actually, I said in the paper, we haven't found that yet.
Yeah. Okay, I get it now.
Great. Thank you for asking that and clarifying.
Questions? Yes.
Yeah, so it's not necessarily a Beyond-CMOS device, but you know, these fields are very adjacent. You know, the spintronics and so on. Yeah.
Okay, maybe a follow-up question to that.
Yes.
At some slide you showed energy delay product for STT-MRAM was like, the delay was like a microsecond or so, 10 to the 6 picoseconds. I was just wondering.
I'm sorry,
like,
what did I say? I'm sorry, could you start
on
again?
one of the slides you showed the graph where there was the energy delay product for also showing STT-MRAM.
STT, I didn't have any, I had just
Or
spintronics.
STT, it didn't say what STT.
Yeah.
Yeah, if you go, I think way before that.
Here.
Oh yes, this one, yeah. So, no, this not doesn't.
Okay, so just.
Oh yeah, it also has delay on the.
Right, delay versus energy.
So this delay is like 10 to the 6 picoseconds. I was just wondering,
Yep.
why is the number so large? It's like a microsecond. What delay is this?
Yeah, this is domain wall. Because probably what is involved with this, there's interconnect involved with this.
Mm-hmm.
So we're building a 32-bit ALU. So you might be in the tens of nanoseconds for the switching of the actual ferromagnet, but then we've got to get the state to the next state, and the dimensions and the propagation, and as I indicated, spin doesn't, and domain walls propagate much slower than electronics. So it would be this is a whole ALU, not, this is going through a 32-bit ALU, not a gate.
Okay, got it, thank you.
One more question?
But the main point is you've got to consider the whole, the physical design, interconnect and switch in doing that kind of thing.
One more question. Something that wasn't clear in these types of benchmarking charts is time.
Yeah.
In other words, we have a roadmap for CMOS.
Oh, yeah.
And according to Intel, that roadmap goes very far. So what does it mean? How far the CMOS points are expected to move? In
Well, the way I'd answer this is, first of all, I think it's not within 10 years, because we have a path, 2 or 3 generations we're working on. Obviously, we'd be irresponsible not to do that for everybody. But it's certainly, there's 2 ways of looking at it. One is, this will become a reality when we have a significant proof of concept and a value proposition that's significant, and that the benefit will outweigh the risk, and that will be adopted, all right? And so the other way I'd also say is we're doing this work, and unless we do this work now, let's say we started this work 10 years ago, we have to give credit to a consortium called Nano-Electronics Research Initiative that was a consortium of it, and they said, let's go look further out for the next switch. They didn't think about all the interconnect and that, but they started. If we hadn't started that work, I think it was 10 years ago, exactly, we wouldn't be today, I wouldn't be standing here today talking about what's the best option to do for the next 10 years, or for next year and the next year after that. So we're 10 years further along than we would be if we said, oh, we've got an energy problem. Data centers growing to 10% of the power consumption of the US or whatever. We wouldn't be standing here working on solutions, but we are. So it's a thing is, if you don't start it, you won't know as much. And so it's a very chicken and egg question, and I get that a lot from management. Said, which is the best device? Tell me the best device. Oh, nothing's better than CMOS. Oh, okay. That's not the story. I mean, I'm saying that there are principles, there's direction, there's potential in this direction. These are the things. So that's the way I'd answer that. So it's 10 years plus, 10 to 15 years. But if it goes faster and we make a breakthrough, it might be 10 years, not 15. It's not 7 years, it's not 5 years, because we have a path for that, and that's too soon.
Thank you, Ian. This was a really great talk. It's great to have you. Thank you very much.